This evening's live demo is about force spectroscopy for nanomechanical measurements. And our presenter this evening is Dr. Patrick Frederix. He heads the application and service team here at NanoSurf. He has extensive experience in AFM, did his postdoc in Professor Andreas Engel's group at the University of Basel before joining NanoSurf back in 2010. So with that, I'd like to hand over to you, Patrick.
Okay, thank you very much, Daniel, and also welcome from me to everyone attending the webinar. As said, in this webinar, I would like to show you how spectroscopy is set up and performed with the NanoSurf software. The beginning part, I will have some introduction slides. Then in the middle part, we will turn to the AFM software, where I can show you how to perform the experiments. And then towards the end, I will shortly also show you our new ANA software to analyze the force curve. But let's first get some introduction slides on force spectroscopy. So why would you want to do force spectroscopy? There is a whole wide range of applications for force spectroscopy. AFM is, of course, famous for the imaging, with down to atomic resolution, but also for larger objects. AFM can make very nice images. But what AFM can do, and for example, electron microscopy or optical microscopy cannot do, is exert force on the sample and measure the response of the sample by the force. This can be interesting for the determination of mechanical properties like the elastic modulus. If you push in a cantilever into a sample, you can see how is this sample responding to that force. And that depends on how elastic is this sample. But you can also, instead of pushing in it, you can also try to pull at the surface or pull cells away from the surface and measure adhesion forces, or chemical interactions between a tip and the surface. And finally, if you go a little bit further away, if you have a molecule tethered between the cantilever tip and the surface, you can also measure the mechanical properties of these molecules while stretching them. So there is a whole wide range of applications for force spectroscopy. But what is force spectroscopy? Bluntly said, in force spectroscopy, you move the Z piezo up and down, and particularly while it's touching the surface, you look how the deflection is changing. It is generally performed in static mode, but there are also other types of spectroscopy, like you can do it in dynamic mode, looking at amplitude and phase, or you can look at the current as function of an applied voltage, so IV spectroscopy. If you look at such a force curve as you see here in the right bottom, it has different phases. So in black, you see the forward curve here. And while moving to the surface, but not yet touching it, the cantilever is unperturbed. You don't see any deflection. The cantilever is flat. And then at the position B here in the chart, the cantilever is snapped into the surface. And then in the next phase, phase C, when you go further down with the cantilever starts to bend up. Normally you do that until you reach a certain force. And when you are at that force, you turn around the movement and move away from the surface again. In the beginning, in the contact phase, the cantilever will be unbending. And then what you generally will see is some adhesion force of the tip sticking to the surface. And there, at the end, you have the highest adhesion force, from which the cantilever snaps back to equilibrium, and then you are back at the baseline level. So they are here denoted by the letters A till F for a cycle. But in principle, initially everything is measured in volts. And that means the microscope needs to be calibrated. You want to know exactly how much you move the z-axis, the z scanner up and down. For that, it needs to be accurately calibrated, or even better, you have a position sensor for z, particularly with piezo's, which may not be perfectly linear. Then you also want to be able to quantify the bending of the cantilever into a force. And that means you need your optical detection system needs to be calibrated to go from volts to a metric deflection. And this calibration depends from cantilever to cantilever. Particularly the length of the cantilever plays an important role, but also where you exactly focus the laser on the cantilever. So this is a measurement, a calibration you need to do every time before an experiment. In addition, you need to know the spring constant of the cantilever. Although all manufacturers give a design spring constant or nominal spring constant, it may deviate from it. And for that, you need to measure the spring constant. So I said to get to the force, we have two steps. The optical deflection system is characterized by the deflection sensitivity, and that converts the voltage output into a metric deflection. How do you do that? You push the cantilever on a relatively hard, incompressible surface. While you do that, your cantilever bends up, but it should not penetrate into the sample. And then you know how much the cantilever bends per nanometer that you move down the Z piezo. The second part is the spring constant, and here Hooke's law describes that for a spring, the force is proportional to the deflection with the spring constant in between. And how do we do that? In our software, we have implemented the Sader method, looking at the thermal noise data of the cantilever. We'll get to that during the live demo afterwards. So deflection sensitivity calibration, I want to shortly go into that a little bit more. Here you see how that is more or less done. You have the forward movement, snap in, and there in the contact phase on the left, on a hard surface, this will be a linear curve, and you can determine the inverse of the derivative of that slope, and that gives you the deflection sensitivity. One part not mentioned before is that in general, the Z position is interesting, but not for the analysis of force spectra. Normally, you want to know how far did my tip enter into the surface, how far did it indent? Or if you're pulling at a molecule, what was the distance between the tip and the surface? And this is not necessarily the same to the movement of the Z piezo. So this is illustrated in the graph here to the left. You see if I move my cantilever from the surface over a distance z away, and there is a molecule theta between the tip and the surface, the cantilever will bend down by a distance delta d, and the tip sample distance is not z anymore, but z minus delta d. And this is called, denoted here with the small Greek letter delta. For the indentation, exactly the same equation holds. If you indent into a sample, you also subtract the deflection. So if I have my cantilever and with the Z actuator, I push it down by 10 nanometers. If the cantilever is deflected by 4 nanometers, it means that the cantilever indented by 6 nanometers into the sample. So you always take the difference between the Z position and the deflection. If you if you do that and you look at the force curves, you can immediately see if a curve has been adjusted or not. On a hard surface, in the contact phase, the curve gets vertical, and particularly at the snap out, you will see that normally the deflection goes in one step from a high deflection to 0. But in this phase, if you look at the tip sample distance, the tip suddenly makes a jump to a larger distance away from the surface, and you get this angled line. So to summarize that, we have a force curve with signals observed in voltage and Z piezo movement. And to go to the force curves, you calculate the deflection in meters and in newtons to put it on the force axis. And horizontally, you correct the piezo movement with the deflection to get the tip sample separation. Here you now see an example of some real curves. Before were just model curves. These are two measurements done on a polymer mixture of polystyrene and polybutadiene. And what you immediately see in the force curves is that they are different. And that is information you immediately get out of a force curve without even having analyzed it largely. So what you see is that the polystyrene has a much steeper slope than the polybutadiene. The polybutadiene is softer than the polystyrene. So the slope immediately gives an indication of the hardness or the stiffness of a sample. You also get an idea of the indentation depth that you have. This is a very important control parameter, particularly if you're measuring on thinner samples where your indentation should not exceed about 10% of the sample thickness. Then you can measure the maximum adhesion force, or you can look at the surface under the adhesion curve, which is a measure of the adhesion work, of the work to be done to pull the cantilever away from the surface. So that gives you some adhesion properties of the tip sample interaction. Of course, the slope and indentation depths that are rough indication of the sample hardness. If you want to have it more quantitatively, you will like to calculate elasticity from the contact part of the curve, and there you can use Hertz models, Snedden, DMT, JKR, and that is done in, for example, in the ANA offline software. A question that's often coming up when we talk with customers is, what cantilever should I take? And the choice of spring constant is very important. And as a rule of thumb, the indentation should be approximately the deflection. If you know what kind of sample you have, here in blue are some examples for biological samples. In red, black is some material science samples. And in the bottom, you see the modulus axis. So you see a little bit how stiff they are. And there you can see which spring constant of cantilever would match the kind of cells that you want to measure, or the kind of sample you want to measure. Eventually, you will have to do a test, an empirical test, to check how is my indentation approximately the same as my deflection. And if the slope is much too steep or too slow, it means that your cantilever is, in case it's too steep, the cantilever is too soft to indent the tip into the sample. Or if the force curve is very shallow, it means that the cantilever is so hard that it only pushes into the sample without being deflected. So based on such curves, you can get an estimation whether you are in the right range. And indentation approximately equal to deflection, whether it's a factor of 10 harder, more or less, that is not so critical, that we can still measure sufficiently accurate. On the market, there are a lot of different types of cantilevers. Particularly in the beginning with the biology, the triangular cantilevers got a lot of interest because those cantilevers gave very high resolution imaging data in the beginning. But for force spectroscopy, both rectangular and triangular cantilevers can be equally well used. Personally, I have a slight preference for rectangular cantilevers because it's a little bit easier to calibrate it, and it is less susceptible to the lateral deflection than a triangular cantilever. Another important part of the cantilever is the tip, and all standard tips for imaging, they are conical. You want to have a sharp tip to get the highest possible resolution. But particularly for imaging, also colloidal probes are very popular. And why is that? In general, colloidal probes give you better quantitative data. You better know the radius of a sphere than the exact opening angle of your cantilever. Plus, a surface of a sample can better follow the contours of an indenting bead than of a very sharp high aspect ratio tip. So the contact area is better defined with a colloidal tip. And what you see here on the right is an example measured in the group of Igor Sokolov, where they looked at cells. They used not the standard Hertz model or Snedden model, but a brush model. And they looked how the elasticity depends on the indentation depth. And what they observed is that for spherical tips, you get a much better, a much steadier result. There's only 5–6% of variation in the obtained values at different indentation depths, whereas with pyramidal conical tips, you have a much larger spread in the obtained elasticity. Nevertheless, there are applications where conical tips have their advantage. And there is a study from Martin Stolz back from 2004, and he looked at cartilage. And on cartilage that has some hard fibers with some softer material in between, and if he used a colloidal probe, he could not see much of an effect on the stiffness during different stages of arthrosis. But with a very sharp tip with which he could actually push between the hard fibers in the softer material, he did see already an effect of the beginning stages of arthrosis, which he was not able to see with the colloidal tips. So there perhaps the absolute value is less quantitative than with the colloidal probes, but with the colloidal probes he was not able to get the data because the resolution was lacking. Colloidal probes, how easy is it to get them? You can now commercially buy them from several manufacturers. Here on the left, you see a commercial product. It's CP stands for colloidal probes, and then the QPS count. That's a cantilever with spring constant 0.01 Newton per meter that you can buy like this commercially. Then you can also glue cantilevers yourself or spheres on a cantilever yourself. It's tricky, it's possible, but you need to know exactly what you're doing. You probably need micro manipulators, a good optical microscope or binoculars with sufficient magnification so that you don't break off your cantilevers while putting the bead on. And finally, it is also possible to reversibly attach a bead to a cantilever if that cantilever is hollow. So we use a lot FluidFM, and with FluidFM you can aspire beads to a cantilever. In the optical image you see an example of a 10 micrometer bead aspired to the cantilever. And the nice thing about this is once this bead is corrugated, you can just remove it by applying an overpressure and then pick up one of the other spheres, colloidal particles on the surface and continue your measurements. Now that for the introduction, let me get towards today's experiment, what I want to show you. Experiments that I will show you are done on FlexAFM with an NIR SLD scan head. The SLD, the light source, has less interferences than a laser, so that is particularly interesting for spectroscopy. I'm using a C3000 controller, and in the C3000 controller, advanced spectroscopy and cantilever calibration options have been activated. You can also do spectroscopy without these options, but it's making it much more difficult and in some samples even impossible. The sample I will be measuring today, it's from our standard spectroscopy mode kit. This sample contains 3 areas. In the top, there is a piece of silica, and the silica is sufficiently hard to measure the deflection sensitivity of the cantilever. In the bottom, with the blue and the black dots, you see 2 pieces of polymer about the same thickness as the silicon, but they have a slightly different elastic module and have also different adhesion properties. So this is the sample that I will show you on the principle of how to do the measurements. Choosing the right cantilever, we know from measurements that these samples are in the 100 to 1000 kilopascal, kilopascal range. And for that, I decided to take a TAP 150 cantilever from budget sensors. So with this, I end the presentation part, and let me now go to the NanoSource software, so which you should see now. And so I'm here in the imaging pane of the software. It's still for operation in phase contrast mode with a dynamic mode 190 cantilever. That's not the one that I want to use. And I can, of course, change all the parameters by hand. But I would like to show you it's also possible to load parameters that have been preset. And now here I can select the spectroscopy air parameter set that I selected. It takes a little bit for all parameters to be set. So what you already see is the mode has been changed to static force mode. The cantilever has been changed to TAP 150 ALG. So that has now all been done. And if you would have a different cantilever, you can still pick one up from the list. The next part is we need to we first go to the spectroscopy pane. So this was imaging, this is spectroscopy. There the layout is not exactly as I prefer to have it. So I can also there go for a predefined chart layout. And for me, it's just the default. And if you do that, it's almost correct. It shows you the deflection signal there in 2 graphs, here as function of the Z sensor, and here at the bottom, as explained before, as function of tip sample separation, because that often is the more important parameter. Here on the left top, you'll see an overview of the scan range, so 100 micrometers for this scanner, and in here I can afterwards select an area to do the spectroscopy. and to this bottom graph you will get to afterwards. But now first things first, I need to calibrate my cantilever. I retract a little bit from the surface, and I generally start with the thermal tuning to determine the spring constant. And that's the nice thing of the Sado method compared to the equipartition theorem, is that you don't need to have a calibrated deflection sensitivity. So I can press start because I selected this cantilever. It knows where to look for it. For the resonance frequency, in orange you see the measured data, the spontaneous oscillation of the cantilever at different frequencies, and at the resonance frequency you get the highest amplitude. We fit the data with an harmonic oscillator, and that is shown in blue, and that gives you back the resonance frequency of the cantilever, the quality factor, and most importantly the spring constant. And you see this cantilever has a spring constant around 3.1 Newton per meter. Once this is stable, I can stop the measurement, and I say yes, that's good value, that's a reliable value, and you say use calculate result, and then this spring constant is set in the software. This cantilever should have had 150 kilohertz resonance frequency and a spring constant of 5 Newton per meter, and here you already see that the values given by the manufacturer may deviate from the actual values that you have in the box. And a lower resonance frequency already indicates that the spring constant is a bit lower as it should be, which is also what we measure. The next part of the calibration is the deflection sensitivity, and for that we have a wizard. Here in the left, deflection calibration. You can set it to default parameters if you're not sure that they are set. And then you can start the calibration. It will automatically approach to the surface. And once it is at the surface, it will take 5 force curves. And then it will take the average value of these 5 force curves to determine the deflection sensitivity. So it's now almost at the surface. Now it is, and now it's starting to move the tip with the Z piezo from retracted to the surface. That takes a little bit more time for the first curve, and then the other 4 curves go a bit faster. There was the first 2 curves already. Here you nicely see the force curves, and now it retracts a little bit. It gives me a deflection sensitivity of 26 nanometers per volt and a standard deviation of 1%, which shows me the 4 curves were quite close, or the 5 curves were quite close together. That means I think, yes, these data are very reliable, so I click finish, and by clicking finish, I accept the used calibration sensitivity, and that is also stored in the software. So now the cantilever is calibrated, and we can start to measure. I will retract the sample a little bit further because I don't want to crash the tip while moving to another area. And now I move down. You see there is the edge of the silicon part. Now I'm above that. The black line you see there is the edge between the 2 types of polymer. I start at this one, go a little bit further away from the edge. And now I go a little bit closer. I have to take care, of course, that I don't break the cantilever. And before I approach, I want to set up my experiments, and also for that we have a wizard. And using the wizard, it starts with, yeah, I want to do force distance spectroscopy. And here I can select different options. If you have standard spectroscopy, you get fixed length spectroscopy, or you can do it for a single point or for a grid of points. And we have discussed this, and we have noticed that if you do one or the other, the behavior of the system should be different. So we gave predefined settings, whether you want to have a single point or multiple points. I'm going to cancel this now because we want to work with the advanced options and a stop by value. And for that, the spectroscopy code should be activated. So here you can always activate codes. They are all in, they are valid, so that should work. And let me go again into the wizard. And now you see I have not 2, but I have 4 options. And you now also have stop by value for a single point or stop by value for a grid. I can then go to the next one, and now you get the main parameters of the spectroscopy, the distance range. I take 2 micrometers. These samples, I know they show quite some adhesion, and the travel length should be sufficiently large to pull the tip away from the surface. I will make the time a little bit shorter to save some time during the experiments, that we don't have to wait too long. And because I don't expect any sharp features, I reduce the amount of points to 250 points. That will also reduce the file size if you have a large map. The stop value, you can have it in volts, but since we have calibrated the complete system, we can also do it in newtons, and I generally like round numbers, so I go 100 nanonewtons, that if I do a second experiment once, that I can nicely reproduce the same settings. The software allows you to have a break, a pause, while you're in contact with the surface. This is interesting, for example, if you do adhesion experiments and where you expect adhesion to depend on the contact time between the tip and the sample. If a cell is hanging on the cantilever, the adhesion of the cell with a substrate will depend on how long the cell is in contact with the substrate. So you can there enable a pause, and during the pause, you can select whether you keep the tip at a constant height or whether you keep the Z controller active. Z controller active is generally the right way to go if you do material science. If you are working with living cells, I generally prefer to keep the cantilever at a fixed height because cells tend to respond to the cantilever pressure, and they tend to retract themselves a little bit. And if I then move after with the cantilever, I push more and more and squeeze the cell more and more, which is generally not what I prefer to do. We are not so much interested now in the adhesion, so I will disable the pause. I go to the next one, and this gives me a summary where parameters are adjusted depending on the settings you did before. So the cantilever is calibrated. The spectroscopy is set up, and now we only have to select where we want to do the measurements. If you did an AFM image before, you can load this image with this button, and you get here to see the topography or deflection signal or amplitude signal of your recorded topography. And otherwise, you just have a blank image like we have now. And here you can either select a single point where you want to do the spectroscopy. You can select a line of points, or you can, and that's what I want to do today, is you can select a grid of points. So the grid is rectangular. I now keep the shift button of the keyboard pressed, and then it's actually a square. once you have defined the square, you can also move it. And again, I like round numbers, particularly if I want to do multiple experiments on multiple samples. I want to be able to reproduce the data easily. And I take them now in the center of the scanner. That means an offset of -40. And then if I take a range of 80 micrometers, it will be nicely centered around the value. And every time I change a parameter, you see that it's modifying the square in the screen. 8 times 8 points. And now you can wonder, hey, 80 micrometers with 8 points. Why is that not 10 micrometers point distance? And that is because at this setting here, the distance between the first and the last point is 80 micrometers. If you want to have the distance between the points, the 10 micrometers, you can select here the cell center, and now you have 80 micrometers divided by 8 is 10 micrometers distance between the points. And now I can just start the measurement. And now it will move from point to point, measuring force curves in each of the points. And the top right, you see the deflection as function of the Z sensor. In the bottom, corrected for the deflection of the cantilever. And there you see 4 red markings in it. The slopes of the forward and of the backward curves on the black and white curves. The lowest point of the deflection in the forward and the backward curves. And now here in this graph, I can actually display one of these parameters. Now let me take, for example, the adhesion. Now you see here qualitatively the adhesion of each of the points. Now it's already almost true. And now I can just click on every pixel and look back at the force curves. It's only showing the forward there. Let me change that we also see the backwards curve. So now we see also in white the adhesion. That one is a bit brighter. So you can compare those curves. You see the dark one has a lower point than the white ones. The graph on the left, it also shows the deflection, but here horizontal you see the z-axis signal. And if I now scroll this triangle, I also see more or less each of the force curves. And I see, for example, this curve there with the very white that has a very strange high background. I can move to that one and see whether I see something special about it. That's not so obvious that something is different with that curve. So it allows you to fastly look whether some of the curves are deviating from the other. So it's in false color, you see the deflection, white, high deflection, orange, close to 0. So that's what you get from this curve. The zigzag shows you also that there is a tilt on the sample with respect to the scanner. If you are at the very first point, you reach at this height, the set point, but on the next line, on the next point, it reaches the surface already a bit earlier until it's at the number 8 point and then goes to the next scan line and goes back, and then you see it's nicely following that contour. And in principle, this you can repeat also on the other samples, on the other area, and then also take a map like that. If you have recorded that map, now 64 points is not so many. You can actually go into the offline software, and that is this one. So here you now see the offline software, the ANA software that we recently brought out. And that allows you to analyze the data and get more quantitative data out. It calculates a modulus based on a model. These data have been measured with a pyramidal tip. So it means we need the Snedon method. We have the DMT, Hertz, JKR, and pyramid or Snedon in. Since there is a lot of adhesion in these curves, we can only use the forward one. I mean, because of the tip shape, we are limited to the Snedon cone or pyramidal rectangular four-sided, but that's almost a similar approach. And these models cannot handle adhesion. So that's why we have to take the forward direction for the analysis. And I have here two graphs where I can select here. So here I now selected the forward of the E module, but you can also look at the minimum, at the slope, the contact point. Gives you there the contact point. There you see the slope of the sampling. So this is more or less topography of your sample. So you can there select these. If you want to zoom in, you can zoom in on a specific area, and then you can say, okay, why is that area brighter? I can click on it and look at the force curve that belongs to that point, or I can go to another point and look at the force curve of that. And then in here, you see histograms of the E module and of the backward minimum, so the maximum adhesion force for this sample that's close to 25, 26 nanonewtons, and an elastic modulus around the 2 megapascal. So that's the soft sample. If I take the stiffer sample, it will reload this data set. So I can there select which data I want to show. And now you will get how it's calculating the data or reading the data. That will take a moment. It's 16,000 points in this graph, so that takes a little bit of time. And here you now see the modulus of the second sample and also the adhesion. The stiffer sample, the previous one had around 25, 26 nanonewtons of adhesion. This stiffer sample has clearly a lower adhesion, maximum adhesion. And the adhesion is also higher. I can zoom in a little bit on the histogram so that you see a bit better where the maximum is. That's between, yeah, that's around 6 megapascal, where we were closer to 2 megapascal with the other sample. If you want to scale back up, you can go back to the original scaling. So this is now new. This is available to all NanoSurf customers for free, so you can contact us. It will be released this month. So then you can download it, and whether you have advanced spectroscopy or not, you can analyze these data. But of course, it makes most sense if you have advanced spectroscopy option with your system. And with this, I would like to conclude the presenting part and then open up the question and answering part of the live demo.
So the first is, how do I know how far to penetrate the material?
That's a good question. There are several parameters that influence that. So if you have a colloidal tip, the indentation should always be significantly lower than the radius of the sphere. The sphere is in the models, the Hertz model, it's approached by a parabol, and that's only valid if the indentation is much smaller than the radius. So if you have a radius of 5 micrometers, stay well below the 2.5 micrometers, then you are safe with the approximation there. In any case, also with a pyramidal tip, if your tip height is 10 micrometers, you should not try to indent 15 micrometers. That is obvious. On the other hand, as I mentioned before, there is a rule of thumb that says you should not indent more than 10% of your layer thickness. If you do that, you start to sense the substrate below. So if you have a cell that is 1 micrometer thick at the cytoplasm where you want to measure, you should not indent more than 100 nanometers. If you're looking at thin layers that are a few hundred nanometers thick, you should not indent more than a few tenths of nanometers. So it strongly depends on how hard your sample is, and you will need to do a few force curves to see what your maximum indentation is, to see whether your force range is good. If you're indenting too much, you have to reduce the maximum force. If you see, I want to have a bit better shape, I want to have more curve, you can increase the force to get a larger indentation and have a larger area to fit.
Great, I hope that answered the question. The next question is regarding the pause that you were talking about in the software settings. Is the pause the same as dwell at maximum force, or is it pause at trigger?
So what you do with the pause is you move until you reach the trigger value. When you reach this trigger value, you stop the movement and you keep at 1 second at that, either at that height of the tip or at that force on the tip. So if you have to, if you want to have constant force, we activate the feedback loop and we regulate the Z piezo to keep that force constant. If you keep the Z height constant, you can do that in closed loop based on the Z sensor. And then of course the force may change during the pause. So I hope that answers the question.
Great, thanks. So here's a long question. First of all, the attendee says, thank you very much for the nice demo. A question about the force curve setting. You set 2 micrometer scanner age with 0.25 seconds per curve at each pixel. Is it the single curve measurement during 0.25 seconds, or has it been averaged over, for example, 10 measurements? In the force curve grid image, the force curve in each pixel looks very smooth with very low noise. Just wondering if this is average data or it is the raw data.
So there's a few questions in there. The time, what we do is the time you set is the time that it would be needed for 2 micrometers distance. So we calculate what kind of speed is that. So 2 micrometers in 0.25 seconds, that would be 8 micrometers per second. So on the way to the surface, we move at 8 micrometers per second for every curve. And there is a slight deviation on that because this is done based on the piezo voltage and not on the sensor signal. So there might be a small deviation. And whether the force curve takes exactly the forward direction, 2.25 seconds, you cannot really predict that. That depends on the topography of your sample. If you go from a low point to a high point, the sample will be reached faster and your time of that modulation will be a bit shorter than 0.25 seconds. On the way back, we will have 0.25 seconds for every curve. Then on the curves in the ANA software, so on the curve in the measurement software, these are raw data as measured without any filtering. In the ANA software, I honestly have to say, I would have to ask whether they do a smoothing or a filtering there on the data. I don't have any noise suppression on, so it may be raw data, but I'm not 100% sure.
So if this, If you'd like a more detailed answer, please just reach out to info@nanosurf.com with that, and we'll get back to you. The next question is, how does the sample approaching mechanism work? How do you know that you won't crash into the sample?
Yes, so during an approach, we can do it manually with the advanced button to get, and then I can use the optical image to get the tip close to the surface. But there you have to be careful, because there you can indeed crash into the surface. During the automatic approach, we look at the deflection while moving the approach motor down. When a preset set point is reached, the approach is automatically stopped, preventing an excessively high force on the sample or even breakage of the cantilever. So we look at the deflection while we are approaching and have an automatic trigger on the deflection.
I have a plant leaf that needs to be measured under fluid. It seems it is a swelling porous media that changes volume rapidly. I can't get a stable spectroscopy map. Do you have any tips how to deal with this application?
That's a very interesting application. I think the secret there is probably time. You have to equilibrate your cells in a Petri dish for a while before you put it on the AFM, so that the cells have taken up the water and they reach an equilibrium, or at least that they have a very slow change in the process. Of course, if you would be interested to look at the dynamic of how is the swelling influence the stiffness of a cell, then you have to be careful. Probably don't take complete maps, just fewer curves or smaller maps. Approach to the sample, do a few force curves, retract to a safe distance, and if you do time-lapsed, wait a bit, do a new approach, swiftly do the next force curves, retract a bit again, and do a reapproach so that you can compensate for the swelling of the cell. And if it's too much, in principle, we have also a possibility of a 100 micrometer actuator that would give you a larger swelling range before you reach the end of the ZPHO.
Is it better to have the deflection sensitivity calibrated first before the spring constant calibration, as with other AFMs?
So if you would use the equipartition theorem, you would have to do it first. There is no way around it. I generally first take the spectrum, the spring constant, because when I start, I am far away from a surface, so it is for me the most obvious thing to do. In principle, for determining the properties, it is not critical whether you do first one or first the other. If you first do the deflection sensitivity and you want to do the spring constant afterwards, take care that you withdraw far enough that the surface is not causing any damping on the cantilever movement, because that would give you a different resonance frequency and a different damping, and may influence the spring constant determination.
What is the maximum resonance frequency that thermal tuning can find out?
That is above the megahertz. So the sampling rate goes to 5 megahertz, and we have had cantilevers where we looked at the thermal tune above a megahertz.
Is that of practical use?
Yes, there are smaller cantilevers, or if you want to look at the higher modes of a cantilever where you are in that range of resonance frequencies.
Okay, thanks. Next question is, what is the maximum scan size you can measure? Is it just 10 micrometers?
No, that I can show you. Let me try to share my screen again. So it shows here 10 micrometers.
I don't see a screen.
It's not, oh, sorry. Now it's showing?
Yes.
Okay. So if I load here the data, yes, now it's 100 micrometers. So closer to the scan range. And now you can get a larger map.
Okay, I hope that answered the question. I have another one. Are all AFM systems capable of doing this type of measurement?
Yes. There is, though, a difference in accuracy that you can reach. So with core AFM, with FlexAFM, you can go to higher resolution spectroscopy. We have a more sensitive photodiode in it. And these systems are able to do thermal tune. But that doesn't mean that you cannot do it with nano AFM or with a system with an EasyScan 2 controller.
Okay.
You can still use there the dynamic force, and then you can use a frequency sweep of the cantilever. And I hope it is showing it. I'm not quite sure now that the cantilever was broken. Yes, we still see there the resonance peak of the cantilever coming up. And it will then also do a fit of these data and give you also back there 2.86. Before you were also in that same range, 2.78, 2.9. So in the same range of spring constant you get with the thermal tune, you can also get with the frequency sweep.
Right, thank you.
And what is, of course, with core and FlexAFM, you can do the spectroscopy on samples in liquid, which is not capable with nano AFM or nanite or lens AFM.
Okay, so it's best to discuss with us which system to use depending on your application.
Yes.
Next question is, why is silicon used for measuring sensitivity of the cantilever? Because we have much harder surfaces.
So for the spring constant here is 5 newtons per meter about, or 3 newtons per meter actually. And that means that if I push with such a small force on the sample, I can still consider the tip and the sample to be non-compressible. Yes, if I take a much harder cantilever to study harder surface, I would need a harder surface so that to measure the flexion sensitivity.
And vice versa, with a harder surface, you need a stiffer cantilever.
Not necessarily. With a very hard surface, you can also calibrate a soft cantilever, but if it doesn't work the other way around.
Next question. How do we choose the scan size in case of polymer solutions?
That's a good question. So a lot of the parameter settings is empirical. So what kind of a Z range do I do? I'm not sure whether they meant Z range or the XY range. Let me first concentrate on the Z range. The Z range depends largely on the softness of the polymer and on the adhesion force. If you have a very soft polymer, you will indent relatively far if you have a high force. That means you need that indentation to be covered by the vertical movement. In addition, if you have a large adhesion force, as you also saw in the force curve that I showed you in the ANA software, the Z range need to be sufficiently long to pull the cantilever away from the surface. This depends clearly on the polymer. On some polymers, you can do with a very small range because you have hardly any adhesion, but if you have the adhesion, you take a longer range. If you want to compare data, I personally prefer always to take the same range and the same tip speeds when doing that. Then to the second part, what is the lateral range you should take? I generally I first map and look at the object sizes in the map and the homogeneity, heterogeneity. And based on what I see there, I can decide whether I need a larger or possibly a smaller area. Probably better to start a bit larger and then, if needed, zoom in.
Okay. Next question. Is it necessary to have the ANA software for this kind of analysis?
No, it's not necessary. You can also use Atomic J. Also, Mountains Map can analyze the data, and a lot of people write their own software, either in MATLAB or in Eiger. And there we have also libraries and documentation on how our NID files are built up, so that you can import these data also in own written scripts. But the ANA software is freely available, so you don't have to purchase it.
Next question. Can we get topography data from force spectroscopy data? Or rather, can we get a topography image from force spectroscopy data?
Yes, you can. So what is determined if you do a fit on each curve is also the height of zero force. And this it calculates the contact point of the force curve with the surface, and on this, based on this information, you get the height at every point of the sample, and that allows you to get a topography. Of course, the resolution of the topography map is generally less than what you get with normal imaging, because you will not easily do a 512 times 512 points force map.
Okay, but it's enough for an indication if you want to know that.
Yes.
So currently the last question in queue. What kind of mechanical properties exactly that we could get by doing spectroscopy?
So what you can get for an elasticity map, you can get an E module of the sample. If you do adhesion force, you can get the work that needs to be done to pull a cantilever away from the surface, or the maximal force needed for that. If you look at polymers, you can do, for example, a worm-like chain fit and calculate the chain length. You can calculate the rupture forces. Yeah, that kind of or persistence length if you have sufficient data. So that's the kind of data you can get out of the spectroscopy data.
Okay, a couple more just came in. So you said you prefer using hollow FlexAFM cantilevers. Is that generally the best option? Would you recommend that to everyone? Or is that just a personal preference?
It's probably a personal preference. So they have their advantage, they have their disadvantages. A disadvantage is that you have them in less spring constant available. You have them in about 0.2 Newton per meter till about 5 or 8 Newton per meter. So that's a limited range of spring constants. If you take commercial cantilevers like the one I showed, QP, which was based on the QPS cont, that has a spring constant of 0.01 Newton per meter. So you can go there to lower forces. What I do like about the FlexAFM approach is that you can get rid of a contaminated bead without exchanging the cantilever. Or if you have different sized beads, you can first do one size, then another size. Or you can have different types of coatings on your beads if you want to study adhesion. So there you are more flexible with those experiments.
Okay, I think we have time for a few more. So if you have another question, you can submit it now while we answer the next one, which is there any difference between force spectroscopy measured through FlexAxiom versus FlexANA?
So that's a good question. So FlexANA, it originated from an automatic measurement protocol. You have a motorized stage where you have an overview camera where you can look at an area of several square centimeters, can select positions on this area, and then move automatically from one area to the next, recording many maps of mechanical data. So you can start it in the evening, and next morning you can come back and check the measured data. the force curve measurement in itself is the same, whether it's measured with FlexAxiom, FlexBio, or FlexANA. That's all the same measurement protocol that is followed. And the FlexANA offline, that is just an analysis program and independent with which system you recorded the measurement. So it can also be measurements done with an IOAFM. You can still process the data with the ANA offline software.
And I hope that answered that. And just one late arrival, how does it work with biological systems?
So in biological systems, I think the big difference is that you're working in liquid. And for me, some things might get more complicated, but some things also get easier. So generally, you can nicely shield electrostatic forces. You don't have a water film because the complete cantilever is immersed in liquid. And that allows you to get to much lower forces. So in air, you can put a 0.01 Newton per meter cantilever in, but because of snap in and water films, you will not get to the very low forces. In liquid, you can get to these very low forces, and then you can, the approach is the same as in air. You can then work either on layers of proteins, unzipping bacteriorhodopsin, for example, or it can be cells, and then you work on an inverted microscope, or in case of the core AFM with the DEMO, the integrated optical microscope, and then you look where the cell is, put the cell under the cantilever, and do a map of elasticity forces, for example, there. And bio in combination with fluid FM, a very popular experiment is cell adhesion, where we have an additional 100 micrometer Z actuator integrated in the stage, so that you can actually go to a cell, suck a cell or aspire a cell to the cantilever, pull the sample away from the cantilever and measure how much force is needed to pull the cell away from the surface. And because we work with an aspiration force there, you can really go up to more than a micronewton of force, which is with chemical binding of a cell to a cantilever hard to reach. But the general approach is the same, whether it's in liquid or in air.
And follow-up question, is it possible to study the force interaction studies between colloidal beads coated with protein and cell?
Yes, yes. So you can do adhesion experiments there. If you want, for example, have antibodies on the beads coated with antibodies, you can do the first measurements with one antibody on the cell and check where you find adhesion points, and then change the bead to one with other antibodies or without antibodies as a control, and check adhesion of the beads of the colloidal particles with the cell at the different positions.
Thank you very much, Patrick. So I think we'll wrap it up here. There's no further questions in the queue right now. So thank you, Patrick, for the presentation, and thank you to everyone for attending, and I hope you enjoyed this hour. Please make sure to visit our website for a schedule of the other upcoming online events. We're having approximately one per week. There's another 3 or 4 to come. You can also find recordings of this presentation there and of past live demos and webinars that we've done. Yes, so thank you very much to everyone, and wishing you a good day or evening, whatever time zone you're in, and we hope to see you again soon.